Hey, Rouse. For lesson 5.2, the plan was for us to create at least one graph together in class, and then most of your homework is actually completing the back of this sheet, 5.2.1. I plan on walking you through some of that and leaving you with some of that to fill in as homework as well. Solutions are always posted on our website and will probably be included on the classroom as well. So let's give it a shot. Okay, what we're going to start doing today, you can sort of, we need to look down the page, is we are going to, let's do the sine curve together, and then you can do the cosine curve on your own. We're going to define a function whose outputs come from the sine ratio of inputs that are angles. So I've got a graph ready to go here that I should probably label. This is going to be the theta axis. This isn't an x-axis anymore. It's an angle theta. Okay. This is really important because all the way up, let's actually maybe just start over here. All the way up over here, if I sketch an angle in 30 degrees, I know that I can sketch that angle in standard position. So here's an angle of 30 degrees, and I could say I could have an x value and a y value. I know that x value and y value will be in the ratio of root 3a to 1a, and my radius is, if my radius is 2a. But my input, my x value isn't root 3a. My x value, I suppose, for the ratio is root 3a. But my input into this function is going to be 30 degrees. So that input is going to be recorded on a horizontal axis. And when I reach 30 degrees here, when I evaluate that the sine of 30 degrees is 1/2, I'm going to put that, let's also label that height right there, 1. I'm going to put a point at, let's say, 30, comma 1/2. That's not a 30-degree angle right there. This horizontal displacement represents a 30-degree angle. Okay? It's a little confusing the first time we see it. Okay, so first time to approach this, I suppose you could always just type this into Desmos, but you're not going to get the experience of calculating these ratios yourself, of seeing the sine SIGN laws that we discovered in the last unit, seeing related acute angles again. So I strongly encourage you to go through this manually. It's not going to take as much time as it looks like, actually. Okay, because if I have an angle of 0 degrees, then I could be passing through the point r comma 0, and the sine ratio, which is of theta, which is the ratio of y to r, is going to be 0 there. I'm not really in a quadrant. I suppose my related acute angle is 0 degrees, but it's not really acute, is it? I suppose I'm on the border between quadrant 4 and 1, but that I'm not in either one of those quadrants. When I draw an angle of 30 degrees, my related acute angle is 30 degrees. Sorry. 30 degrees. I am in quadrant 1, where my x values and y values are positive. So since the r value is always positive, the ratio of y to r is, of course, going to be 1a to 2a, which is always going to simplify to 1/2. I'll keep as many of these as exact as I can, but for graphing purposes, I might want to do some decimal approximations. Okay, let me get a couple of these values down, and then I'll scroll down to the graph and show you me plotting them. That way I won't have to jump back and forth again and again and again. 45 degrees is in the first quadrant. It has a related acute angle of 45 degrees. Let's draw a sketch in standard position of an angle of 45 degrees, and notice that that creates a right isosceles triangle. It would be heading through the point, the terminal arm would be heading through the point A comma A. Its radius would be root 2a from a Pythagorean theorem there. So the ratio of y to r, where y is going to be positive because I'm in the first quadrant, is going to be given by the ratio of a to root 2 over a, which is exactly 1 over root 2, which I think I'm going to approximate right now to 1 divided by the square root of 2. That's about 0.707. What? Excuse me. Sorry. Sketch an angle of 60 degrees in standard position. And notice we shouldn't have to pick up a calculator until our approximation. This is half of an isosceles triangle, so let's make the radius 2a. That would have been bisected, so that's a. Pythagorean relation tells me that my height would be root 3 times a. In the first quadrant with a related acute angle of 60 degrees, My sine ratio is going to be the ratio of y to r. Root 3a to 2a is going to simplify to root 3 to 2. And since I don't know where to put that on a graph, I'll pretend I don't know that. Divide them properly and get error 2. I divide again and I get about 0.866. And then when I get to 90 degrees, 90 degrees is really when SOHCAHTOA started to break apart. Same thing with 0 degrees. I don't see a triangle here. I need to use XYR definitions. Terminal arm along 90 degrees would be passing through the point 0, r. The ratio of y to r then is going to be the ratio of 1 to 1, or 1. That's why my sine ratio has a maximum of 1. Again, 90 degrees isn't really an acute angle. I suppose I would say the related acute angle is 90 degrees. It's not something I plan on quizzing you on. This is technically on the border between quadrants 1 and quadrant 2. It is not in either of those quadrants. Let's plot those values just to get a start on our curve, and then we'll come back up for some more. So, excuse me. I plot a point at 0 degrees, 0. I plot a point at 30 degrees, 1/2. I plot a point at 45 degrees, it was 1 over root 2. That's 0.707. This is where I like to think of trig ratios as percentages. They are numbers, but they are also ratios, and ratios can be written as a percentage. This number up here that you can't see anymore of 0.707 is telling you that you are 70% of your way up, roughly. So 45 degrees, that's about 75%. Let's call 70% about there. At an angle of 60 degrees, which I'm going to estimate, well, it's about 2/3 of the way to 90 degrees. It's about there. I should be about 86% of the way up, 87% of the way up. And after 90 degrees, I am 100% of the way up, like that. Okay. Now, let's see why doing the rest of this table shouldn't really take us too long. We're actually done with our calculator right now, if you can believe it. Because we can use our understanding of the XYR definitions and related acute angles. An angle of 120 degrees, for example, is going to have a related acute angle of 60 degrees. It's in the second quadrant, and in the second quadrant, my y value is positive. So the sine of 120 degrees is going to be related to the sine of 60 degrees. Isn't this a 60-degree angle right there? So this would still be a half of an equilateral triangle, except my x value is now negative, while my y value is still positive, which is why my ratio will still be root 3 to 2, or again, about 0.866. At 135 degrees in the second quadrant, I have a related acute angle of 45 degrees. The sine of 135 degrees is the same as the sine of 45 degrees. This is kind of like the ambiguous case of the sine law. If I tell you that the sine of an angle is 1 over root 2, you don't know if that angle is acute or obtuse, assuming it's a principal angle. So I just get to repeat these heights again. An angle of 150 degrees in the second quadrant has a related acute angle of 30 degrees. That will give me the exact same sine ratio as the sine of 30 degrees. And if I draw an angle of 180 degrees, then I technically have, I guess, well, not technically, I would argue that you have a related acute angle of 0 degrees. Your y value is going to be 0, so the ratio of y to r is going to be 0 again. Notice a little bit of symmetry. This isn't really repetition. This isn't y values repeating over a constant interval of theta. This is just y values occurring again. They occur again on the way down. This curve is about to change direction. Where is that curve? There it is. So we pass through 120 degrees, 0.866. So we're symmetric there. We have an axis of symmetry of x equals 90 degrees. We pass through 135 degrees, 0.7-ish. We pass through 150 degrees, 1/2. And we pass through 80 degrees, 0. So we should have a symmetric curve here. I'm not so sure that mine is looking that great here. Okay, let's continue. 210 degrees in the third quadrant. Let's just draw this one so that we can see it. It's going to have a related acute angle of 30 degrees. It is 30 degrees past the negative x-axis, right there. That's going to give me one of those a root 3a 2a triangles, except both my x and my y values are negative in the third quadrant. My sine ratios are negative in the third quadrant. So if this is negative root 3a and this is negative a and that's 2a, then the ratio of y to r is going to be negative 1/2. The absolute value of the sine of 210 degrees is the same as the sine of 150 degrees, which is the same as the sine of 30 degrees. It's sine, S-I-G-N, is the opposite, though, because your y value is negative. Notice how SOHCAHTOA doesn't really work here. I mean, I hope from the last unit you're done trying to use SOHCAHTOA. 225 degrees in the third quadrant. Actually, this is in the third quadrant as well, isn't it? This is going to have a related acute angle of 45 degrees and of 60 degrees. So the sine of 225 degrees is going to be related to the sine of 45 degrees. It's not going to be the same. In our previous unit, you would have been sketching this angle in standard position and then just using the fact that its related acute angle is 45, labeling your x, y, r's, making sure that you get the signs correct, S-I-G-N, S. But now I know it's just going to be the opposite of this value, negative 0.707. This is going to be the opposite of that value. You can check all of these with a calculator if you like, but I don't think you should be convinced by your calculator telling you these facts. Sine of 270 degrees, that would pass through the point 0, negative r. The ratio of y to r is going to be negative r to r. That's going to give us a minimum value of negative 1. And then we go back up. Our terminal arm approaches the x-axis again. We have a related acute angle of 60 degrees, and then 45 degrees, and then 30 degrees, as our terminal arm rotates around and around and around. In the fourth quadrant, our y values are still negative, so we should expect the exact same ratios to occur here. We will have a ratio of negative 0.866, negative 0.707, negative 1/2 or 0.5, and then back up when we perform a rotation, a full rotation of 360 degrees, our y value is going to be 0, so the ratio of y to r is definitely going to be 0. See how symmetric you can get your curve to look. Where here, if you go right 30 degrees, you should go up 1/2 of a unit. If you go left 30 degrees from 180, you should go up 1/2 a unit. If you go right 30 degrees from 180, you should go down 1/2 a unit. If you go right 30 degrees from 360 degrees, you go down 1/2 a unit. So like there's your related acute angle now. Now that your theta axis is horizontal, you don't see the related acute angle as being like, I don't know. It's not that rotation there. There's no terminal arm. This isn't a standard position graph. Your related acute angle is actually there or there or there. What are we going through? Here's a related acute angle of 45 degrees, down about, if this is negative 1, negative 0.7, 86, 87%, 100% of the way down. 86% of the way, 70%. Now, I do want you to type this into Desmos, and we'll discuss the specific curvature in a little bit more detail tomorrow, because this should not look linear. It's also not vertical at the origin. You should be drawing a smooth curve that is always changing shape. It's not parabolic either. It's not vertical at the origin, but it does do something called inflecting at the origin. My curve is getting steeper here, steeper here, steeper here. This is the steepest it will be in a negative direction. I inflect there and I stop becoming steeper and I start becoming shallower, but it's not vertical. I'm going to ignore the precision of my points because I think an appropriate curvature is more important. Never linear. So you're not drawing like Homer Simpson's hair or Charlie Brown's t-shirt, not like that. It's not semicircular, it's not vertical. Not semicircular. It's never vertical. Sometimes students do this. They just draw a semicircle and then a semicircle and then a semicircle and then a semicircle. It's not like that either. Okay, it's a nice smooth curve. And it doesn't stop here either. This is again why I don't like having students tell me that the y-intercept is where the curve begins, or let's right now adjust. I don't want you to tell me that the sine of theta, y equals the sine of theta, starts at a height of 0, because it doesn't. It exists to the left of here. When did it start? It hasn't really ever started. It'll go right forever as well. If you want to put in 390 degrees right here, 390 degrees has a related acute angle of 30 degrees. It is coterminal to 30 degrees. So of course the sine of 390 degrees is going to be exactly the same as the sine of 30 degrees, which is going to be 1/2. This curve just continues over and over again. Its outputs are going to repeat over a constant interval of the input. It is going to be a periodic function. I think I might be done with this. Well, I don't know. I'd say I'm done with the chart here. Let's do just maybe a little bit more with this chart. An angle of negative 30 degrees has a related acute angle of 30 degrees. It's going to be in the fourth quadrant. The terminal arm will be. The sine of 30 degrees, negative 30 degrees is going to be negative 1/2. This is going to be negative 0.707. This is going to be negative 0.866. This will be negative 1. And you could probably predict those values were going to occur, because doesn't it look like this curve should be heading down now and then looping back up again? Let's go to -1 and 0. When we start sketching these faster, and for 5.3, we'll probably just plot these 3 key points on a half cycle. But for today, I really want you to reflect on the fact that it's not linear. If it was linear, then after 45 degrees, you would be half the way down. It is faster than that at the start. It only takes 30 degrees to go half the way down. It takes the next 60 degrees to get the rest of the way. On your way up, it takes 60 degrees to get half of the way up to the axis of the curve. In the last 30 degrees, it goes the rest of the way. Its speed is always changing. So it is steeper here, concave up, but steeper there, and then shallower here. That's a little too linear for my taste, but you should be doing this in pencil, by the way. Getting steeper, always getting steeper here. Steeper, 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 steepest, inflect, maximum, axis, 30 degrees down, half the way up, 30 degrees back, half the way up. And there you go. I'll be showing you some animations for lesson 5.3. But the problem with a lot of these animations is that they only show one cycle. And so students often think that the sine curve is just this, but it's not. It does go left and right forever, and Desmos will do a better job of that for you. Although I might want to show you how to get your Desmos settings just right. I'll probably do that for lesson 5.3. Okay, let's take a look at some of the questions on the back and see how we do. Do generate your cosine curve. It's a little bit different. Let's see. Is y equals the sine of theta a function? Let's again get some more practice with our definition of a function. For any input, there for this specific ratio is only one ratio. Sorry, for any, I should be specific, angle. The angles are my inputs. There's only one ratio of y to r. To r. And there's a one-word answer that you can use to answer question number 2. Why are these functions that are defined by trig ratios periodic? Coterminal is what you can say. So if I look at f of 30 degrees, it's going to be equal to f of 30 degrees plus 360 degrees. It's going to be equal to f of 30 degrees minus 360 degrees. In fact, in a more general case, I can say that f of theta is going to equal f of theta plus 360 degrees n, where n is any integer. This is getting a little bit fancy. This is getting close to the unit on discrete functions that we probably won't have a ton of time for in this course. But it basically says any integer multiple of 360 degrees, your original period, your definition of one full cycle. This will give you coterminal angles, and coterminal angles will have the exact same ratio. And that's why they repeat over and over again. Right. The period of our curve. Take a look at the back of your curve and make these same predictions with me. Let's just make sure that everyone's on the same page here, and then I'll let you answer the rest on your own. The period of an original sine curve or a cosine curve. This is actually true. Yes, all of these statements are true for f of theta equals sine of theta and g of theta equals the cosine of theta. Your period will be 360 degrees. Your maximum will be 1. Your minimum will be -1. Your domain is unrestricted. Your range is restricted. I'll call it y values inclusively between -1 and +1. Your equation of the axis of the curve is the original x-axis, y equals 0, and your original amplitude is 1. Okay? Try out the rest on your own. Question 7 is a little bit of extension, but see how you do on your own and try it out. And question 8 is going to help you for dealing with applications. All right. Next lesson, we'll take a look at some technology and talk about how we can use a unit circle to help us sketch these more accurately.